Our last section in chapter 13 deals with buffer solutions. Buffer solutions are very, very important biologically, and we'll explain why in a few minutes. But buffers are solutions that contain a weak acid and its conjugate base. So in other words, we take something like acetic acid and its conjugate base, sodium acetate. And we add both of these to a solution. Now, why do we make the solution up in that way? Well, because this solution has both a weak acid and its conjugate base, these solutions are able to resist large changes in pH when an acid or base is added. So let's look at how that works. So let's say we've made a buffer of our acetic acid and sodium acetate, and then we add a strong acid to it. So if we add an acid, a strong acid will react with a weak base, sodium acetate. And so the result is we form a small amount, or an amount of the weak acid comparable to the amount of strong acid that we added, plus a salt. So adding a strong acid results in an increase to the amount of the weak acid. And we get a similar result if we add a base. So we could add something like sodium hydroxide, and that'll react with the acetic acid, which is the weak acid, to form a small amount of the weak base, sodium acetate, plus a byproduct, which here is water. And there's many important examples of buffers, but probably the most important example of a buffer is one that exists biologically. And that's the buffer that we have in blood. So blood contains a buffer system. which keeps our pH around 7.40. Now, we all the time eat foods that are both acidic as well as basic. You can probably think of many foods that are acidic. Can you think of any foods that are basic? It's actually pretty hard to think of foods that are basic. There aren't many out there. Raw eggs, I believe, have a basic pH. And obviously baking soda does, but that's not something you usually eat pure. But very few foods have basic pH. But regardless, we eat acidic foods, especially, all the time. Yet, the pH of our blood doesn't change by that much. How much of a pH does it take to have a negative effect on you? Well, if your blood were to go about 0.5 off, whether high or low, that can have very, very severe health consequences, could even end up killing you. Yet we eat all these acidic foods, and we're fine. And the reason is because of these buffer systems. So we eat acidic foods, they react with the weak base in the buffer, and the pH of our blood doesn't change much at all. So let's look at an example of that. And the example we could look at is a phosphate buffer. Phosphate buffer is commonly made up of hydrogen phosphate and dihydrogen phosphate. Which one's the acid and which one's the base? With acetic acid, it was pretty easy to figure out because it has the word acid in its name. But here they don't. Well, if you think about the definition of acid and base, acid being a proton donor, then the compound that has more hydrogens is going to be our acid, and the one with less should be our base. So let's think about two situations right now. We're going to add 0.01 moles of HCl. Now, is that a lot? Well, if you calculate that out by mass, this is approximately 365 milligrams of hydrochloric acid. We're going to add it to two different things. We're going to add it to 1 liter of water. And we're going to add it to 1 liter of the phosphate buffer. Now, what are the initial pHs for each of these? Well, for the phosphate buffer, that's something we'd have to look up. And we find that it has a pH of about 7.21. And this is assuming that we're using equal concentrations of the acid and the base. That's not something that we have to do, it's just for this example we will. What's the pH of the 1 liter of water? Well, that's right at 7. Now, after we add 365 milligrams of hydrochloric acid to our 1 liter of water, we end up with a solution with a pH of 2. Very, very big difference in pH. But in the case of the phosphate buffer, our 7.21, because the buffer is present, only gets reduced to 7.12. So not a significant change at all. And so we can see by having this buffer present, we've been able to resist this significant change in pH. Now, how do we find the pH of a buffer? So how would we actually do this? Well, let's look at the following. So here's the same generic acid reaction with water that we started with for looking at pKa. And we're going to go to the same equation that we had before. Ka is equal to A minus times H3O plus over HA. But here we're looking for pH. And to get pH, that means we're going to need to get this term, our acid concentration, by itself. So let's bring the H3O plus by itself. And so we can say that H3O plus is equal to Ka times HA over A minus. But in order to make this pH, we're going to need to take the negative log of both sides. Well, the negative log of H3O plus, that is our definition of pH. On the other side, though, we can split up what's inside the log by adding them. So negative log of Ka minus log HA over A minus. But the negative log of Ka, that's just our pKa. And then the most common form that we see this equation in is to get rid of the negative sign. To get rid of the negative sign, we can just flip whatever's inside the log. And as a result, we get that pH is equal to pKa plus the log of the conjugate base over the weak acid. And this is known as the Henderson-Hasselbalch equation. Now, one of the useful things we can do with the Henderson-Hasselbalch equation, in addition to sort of the obvious, calculating the pH of a buffer solution, is that we can actually use buffers to determine pKa's. So previously we defined the equivalence point. And remember, the equivalence point is the point where we've added enough base or enough acid to completely neutralize all of it. So what is the half equivalence point? Well, the half equivalence point is basically half of the equivalence point. And so at this point, we've added enough to neutralize half. And so we end up in a situation where the concentration of our weak acid and of our, if it's conjugate base, are equal. And again, that's because we've added enough to neutralize half of our acid or half of our base. Well, if A minus is equal to HA, what does that do to our Henderson-Hasselbalch equation? Well, it makes pH is equal to pKa plus the log of A minus over HA, but if A minus and HA are equal, then that's the log of 1. What is the log of 1? The log of 1 is 0. And so at the half equivalence point, and only at the half equivalence point, the pH and the pKa are equal. So what this lets you do, and we looked at a graph like this earlier, where we plotted pH versus amount of base added during a titration. That graph often looks something like this. And it's right about here that we get our equivalence point. So if we find our half equivalence point, which would be half that volume of base, which might be approximately there, then the pH at that point tells us what the pKa of our acid is. All right, so let's do some calculations now. So here we want to find the pH of a solution that is 0.30 molar sodium acetate and 0.70 molar acetic acid. So here's another way that we can identify which one is the acid and which one's the base. Kas and pKas correspond to acids. So the substance that the Ka or the pKa is given for, by definition, pretty much has to be the acid. So the pH, that's what we're trying to find, is equal to the pKa. That's not given, but the Ka is, so we take the negative log of the Ka plus the log of the base, 0.30 molar, over the concentration of the acid. And if we calculate that correctly, we get 4.37. All right, so these calculations end up being fairly straightforward. It's just like many other calculations we do. We figure out what we know and then figure out which term of the equation we need to solve for. But what we really want to be able to do with a buffer is determine what happens when we start adding things to it. So let's try the following then. So now we have a buffer made up of acetic acid and sodium acetate again, and this time both of them are 0.3 molar. Now what we're going to do is add some hydrochloric acid to it, and specifically 0.1 molar hydrochloric acid, and we're adding 100 milliliters. So what will the pH be after that addition? We might even want to calculate the pH that we start with. So what's our initial pH? The initial pH will be the pKa, 4.74, plus the log of the base concentration over the acid concentration, and that's going to be 4.74. Now, before we get into this problem at all, there's an important question to ask. And again, I try to talk about this as often as I can, but a reminder. Should the pH of this solution go up or down? Well, we're adding an acid. So the pH should go down. And in fact, if you get an answer greater than 4.74, then you've done something wrong. All right, so what's the reaction that's taking place? Well, we've added HCl, so that's going to react, and we always assume that all of the strong acid or the strong base that we add will react. That's going to react with the sodium acetate. And it's going to form some additional acetic acid and some sodium chloride. Now, I'm not going to worry about the sodium chloride, that's not important. But we need to figure out how much we start with, how much it changes, and how much we'll have at equilibrium, or after the addition. So go back to the previous slide, and at that point you should be able to calculate the number of moles of the acid, the acetic acid, the sodium acetate, and the hydrochloric acid. And you should be able to do that because in each case there's a volume given as well as a molarity. So just to summarize again, the initial pH was 4.74. After we put our new concentrations in, we were able to calculate our final pH, and we can see it didn't go down by very much, but we did get a slight decrease from 4.74 to 4.71. Let's do one more. All right, I'm just going to go back through that last part again because I believe I may have had myself muted. So you can see here again, we calculated our new concentrations. HCl, our strong acid, reacted with the weak base sodium acetate. So those both went down. The amount of acetic acid went up. We calculated the new concentrations based on the new volume of 1.1 liters. And then we used that to calculate the pH. So again, we're going to do one more of these, and that's this one here. So take a few seconds and think about how we might approach this, and then we'll jump in and work on it. All right, so the one piece I forgot to put in here is that the pKa of the acid here is 4.20. Now, which one is the acid? Again, it's going to be the one that has more hydrogens. All right, so let's determine what's going on here. We're adding HCl again, so we expect that the pH is going to go down, and we can calculate that initial pH is equal to the pKa plus the log of the base over the acid, or 4.20. Now, given that we're adding acid, again, it's going to react with the base, and let's write out the equation for that. So HCl plus C6H5CO2 minus Na plus, that's our weak base, reacts to form C6H5 CO2H plus NaCl. As we did before, we can calculate the amounts in terms of moles that we start with. For our buffer components, we had 0.2 moles. And as before, we don't have to worry about our salt. That's not relevant at all. How much HCl did we start with? We start with 0.075 moles. So remember now, all of the acid is going to react. And it's going to react with the weak base. So we have to subtract that as well. And that's going to increase the amount of the acid. So the HCl, there's none left, as expected. The amount of the base goes down, and the amount of the acid goes up. Now we can calculate the new concentrations for both the acid and the base. Is the number of moles divided by the volume. Again, remember that the volume goes up because we've added more solution. So the new concentration of the base is 0.0617 molar. We do the same thing for the acid. Using the new number of moles over the new volume. And we get 0.136 molar. Finally, we can calculate the final pH as being the pKa plus the log of the final concentration of the weak base over the final concentration of the weak acid, and we get a new pH of 3.86. So as we can see, it did go down as expected, and even though we added a lot of acid here, we still only had a change of just under 0.35 for our pH. So that finally is the end of the lectures for Chapter 13. From here, you should do in-class exercise number 22, looking at buffers. And then we have just one chapter to go.